What's up everybody? In today's tutorial, you are going to code up a policy gradient agent in the Keras tutorial. We're going to tackle the Lunar Lander environment, and as a bonus, you're going to get to see how to code your own custom Keras loss functions, which is a non-trivial affair. Let's get started. So we start as usual with our imports. We want to import our layers, which will be dense for the neural network, activation for an activation function, and input as an input layer. We will also need to import model to construct our model, as well as load model to handle model saving and loading, or loading more specifically. We will also need an optimizer. In this case, we will be using Atom, though you could use stochastic gradient descent or any other optimizer that you choose. I tend to lean on Atom because it makes life easy. We also need to import the Keras backend, and this gives us access to a bunch of functions that are native to Keras, like clip, as well as log and mean or sum, stuff like that. So very important. We want to import numpy as NP as usual, and that is of course to handle numpy type stuff. So we are going to stuff virtually everything inside of an agent class, and with Keras you don't need to have any specific any inheritance from any base Keras classes like you do with, say, PyTorch. So the first thing we want to pass is a learning rate alpha, a discount factor gamma. If you're not familiar with reinforcement learning, gamma is how much the agent chooses to discount future rewards, and it is a value bound between 0 and 1, typically something like 0.99 down to 0.95. For Lunar Lander, we're going to have 4 actions as our default, and we're going to have some default sizes for our layers. We will say, I don't know, it doesn't really matter. We'll say 16, layer 1 size, layer 2 size equals 16, and input dims will give, I don't know, a default of 128. And we also want a file name, something like reinforce.h5. That is to facilitate saving our model. Not so important with the Lunar Lander because it executes quite quickly, but very important for other more complex environments. So of course you want to save all of your member variables in their respective fields. Learning rate, we're going to need something called G. G will be the discounted sum of rewards that follow each time step. We'll get to that later, but it basically tells the agent how much reward it received after any given time step. FC1 dims and FC2 dims, layer 2 size. We also need an actions, and this is of course for our action selection. The policy gradient agent does have a type of memory. We're going to handle these as 3 separate lists. We don't really worry about resulting states in this particular algorithm like we do with, say, Q-learning. And these are going to get cleared out at the end of every episode because this is a Monte Carlo method, meaning it doesn't learn with each time step, which would be temporal difference learning like Q-learning. This is Monte Carlo that learns at the end of every episode, and we're going to discard all of the memories. Now, we could do a batch of episodes, and some people do this, and you probably would get better results with this environment if you did, but just for now, we're going to do a single set of episodes as our batch. So we'll need policy, which is of course the agent's probability of choosing any given action. It is in some state, given it is in some state S. It is a probability distribution. It is what we are attempting to approximate by our deep neural network. And predict will be a separate function that we will use to select actions. We need 2 separate functions because the calculation of the loss requires something called the advantages, which are just the rewards. It's related to this quantity G up here, whereas the predict function doesn't need that. It just needs the current state. And we'll use a function called build policy, or say build policy network. That takes alpha and actions and input dims, layer 1 size, layer 2 size. I'm going to use poor formatting here just for the sake of saving time. And we need an action space. That is the set of all available actions for the agent. Arrange and actions. and we will have a model file as well. Okay, so that is our initialize. Let's do our build policy network function. Build policy network. That takes in self, learning rate, and actions, input dims, L1 size. I'm going to abbreviate it here, L2 size, and that is it. So we need to declare our input layer. That is from Keras. That is the layer we import at the top, and that is takes a shape as input, and that must be self.input dims, comma. That indicates it takes a batch. We also need the first dense layer, dense self.fc1 dims. You know what? Now that I look at it, we don't actually need any of these because we're referencing self. So let's just do this to make things nice and neat. Sorry, I tend to modify these things on the fly because, well, you can always improve, right? So self.fc1 dims, and that acts on input. We also have to declare an activation equals relu. There's no 0 in there, sorry. And that does indeed act on input. We need layer dense 2. That's also a dense that takes self.fc2 dims activation relu, and that acts on dense 1. And then finally the probs, the probabilities, equals a dense layer, and that takes self.n actions as output. We don't specify inputs for the dense layers because they're inferred based upon the input to that layer. And the activation here is going to be a soft max, and that of course takes dense 2 as input. The reason we want a soft max is because we are calculating a probability distribution, and the sum of the probabilities over all possible actions has to be 1, and soft max has that exact property. Now we come to something kind of interesting. So Keras doesn't have an appropriate loss function built in, so we have to write our own. So you do that by using a closure where you wrap one function inside of another. In this case, it's going to be 2 closures. We're going to wrap the custom loss function within the build policy. And the reason is that we don't need to access that function anywhere else from the class, in the class, so there's no point in putting it as a class function. And syntactically, the Keras framework always requires that this has this form y true and y pred, as in y predicted. So you must always have that, otherwise it will complain. And out equals k, at least I believe it will. I haven't messed around with it enough to know, but if I'm wrong, please correct me in the comments. But my understanding is it has to be y true, y pred. So since we're going to be dealing with a log likelihood, we don't want to be taking the log of 0, right? That would be bad. So we are going to use a clip function to clip y predict to a minimum bound of 1 by 10 to the minus 8 and a maximum bound of 1 minus 1 by 10 to the minus 8, the minus 8, yes. And then we will do our log likelihood. That is y true multiplied by k.log of output. And then we want to return another Keras function, k.sum minus log likelihood times advantages. So advantages is something else we have to pass in. We'll get to that in 1 second. So here, this is a double closure. We're enclosing one function. I guess it's only a single closure. We're using one function to return another. And these are all scoped within the build policy network function. So pretty handy stuff. That's how you handle the custom loss functions in Keras. So policy equals model. Let's see, and the input is a list of input and advantages. The advantages are what we're going to calculate using this G up here. We'll get to that in a little bit, but the advantages tell us the reward that followed taking a particular action at a given time step. So it kind of tells you how much reward or what is the advantage of any particular action. And the output of the model is just the variable probs. So that connects the inputs and all the layers within the model. Then we have to do policy.compile. Optimizer equals atom with a learning rate of self.learning rate, and the loss is custom loss. You don't want to use the parentheses here, otherwise it'll expect arguments. It's just custom loss as like a variable instead of a function. And predict will be a model with input equals just the input variable, or layer rather, and the output will be the probabilities. And we want to return the policy and predict models. So that is really it for the definition of our policy network. Now we get to the more interesting stuff of choosing actions, storing transitions, and learning. So let's start with choosing an action. And that takes an observation as input. Of course, observation is passed in from the environment. So we want to do a recast. We want to reshape the array. So using numpy, new axis, comma, everything. Good grief. And what that will do is it will add in a batch dimension along the first axis. And that kind of makes it line up with this here. That is because when we are doing the learning function, we're going to be passing in a batch, the whole state memory of the episode, whereas when we're selecting an action, we only want to pass in a single observation. So you have to keep the shapes consistent. That's why you have to do the addition of the new axis. So probabilities will be self.predict, kind of redundant there. Pass in the state and take the 0th element because it returns a tuple. And these is the output of our model. It tells us the probability of selecting each of the actions given we're in some state S, and of course in some state, and of course they have to sum up to 1 per the softmax function, as well as basic definitions of probability, right? Be random.choice, self.action, space. If you didn't know you could do this, you can specify the probabilities for the random choice in NumPy, and that's precisely what we're doing here. We're using our policy to calculate the probabilities and saying, hey NumPy, do a random action specified by the probability distribution that we calculate. Very, very cool. And then at the end you want to return the action. Okay, that's pretty straightforward. So next let's handle something else pretty straightforward. Self, observation, irrigation, action, and reward. This handles the interface with the memory. Self.action memory dot append action, self.state memory dot append observation, and self.reward memory dot append reward. Very straightforward. Now we come down to the learning function, and this is where all of the magic happens. So what we're going to do here is we are going to iterate over our memory of the episode and calculate the returns that follow each time step. Those returns tell us the advantages or the weights to weight our log likelihood probabilities in our cost function. The reason we do that is because we want to tilt the probabilities in the direction of the actions that give us the most advantageous actions. Makes sense, right? So let's do this. State memory equals numpy array self.state memory. We're just going to turn it into a numpy array to make life easy. Action memory numpy array self.action memory. Perfect. Next, we have to take the actions and turn them into a one-hot encoding. So we can do that like so: numpy zeros, len action memory, and comma self.n action. So yeah, length of memory by number of actions, and then say actions sub mp dot a range. That gives us the indices. Len of action memory, comma action memory tells us the indices equals 1. So that'll give us a one-hot encoding, and that is necessary for passing in the labels to the loss function because it requires the labels to be one-hot encoded. So now we can calculate the rewards that follow each time step. Zeros like reward memory. For t in range len reward memory. So we're going to iterate over our, let's call this t instead of r. We're going to iterate over our memory and calculate what is called the sum. That is the sum of the rewards that followed each time step. We have to take into account the discount factor because we want to discount rewards that follow each time step by a little bit more, and the reason is that our action selection is probabilistic, and so We may have chosen that action in this particular instance, but in another we could choose a totally different, another similar episode, we could choose a totally different action because we're using a probability distribution. And in general, those probabilities will always be finite. They won't necessarily go to 0. So that is accounted for by the discount factor. K in range T, len of reward memory. So this will start at the tooth time step, start at the tooth time step and go all the way to the end of the episode. So G sum plus equals reward memory sub K. So this will add the reward at the kth time step multiplied by the discount factor. And then you want to multiply discount by self.gamma. In the end of each of those, you want to set G sub T equal to G sub sum. And at the end of all steps in the episode, we want to scale our rewards. This promotes stability because the rewards in general can have very different rewards. And as you know, neural networks don't like unscaled inputs. So this is called this algorithm, by the way, is called reinforce with baseline. So this is the baseline, the mean, and standard deviation, np.mean g, and the standard deviation is the standard deviation of g if g is greater than 0, else 1, because the standard deviation could be 0. You don't want to divide by 0, right? Don't cross the streams. That would be bad. Self.g equals g minus mean divided by standard deviation. So that handles the calculation of the discounted for future rewards that follow each of the t time steps with our scaling and normalization. So let's say cost equals self.policy train on batch, and we pass in the state memory. That's our input, as well as self.g. Self.g is our advantages. And we have actions. I just called it actions, so that those are our actual labels. This will be the y predicted, and these will be the y true for our loss function. Once that is done, we are done with our memory for the episode. So let's go ahead and reset it. No point in keeping it around. This is, after all, a Monte Carlo method, and same for the reared reward memory. And that is it. If you want, you can return the cost. If you want to kind of plot the cost over time, if you're into that kind of thing, you can do that. Next, we have a save model. Self.policy.save, self.model file, def load model, and self.policy equals load model, self.model file. Of course, I'm looking at it like the colors are all wrong. I wonder what I did wrong. I added in an extra 9. Okay, so this is 90 lines of code plus some white space, right? Plus minus some white space. So this is a pretty short program, and this handles the policy gradient algorithm in Keras. This is very straightforward. The highlights, just to go back over it, are this custom loss function. When you do that, remember you have to pass in y true, y predicted. This is a closure, so you're going to use this function to return an actual Keras function, and that is the k sum of the negative log likelihood multiplied by the advantages. The log likelihood is what we calculate here, and of course I use the clip function to make sure we aren't taking the log of 0. And we specify advantages in the input to our policy, and of course the advantages are calculated down here by this chunk of code. So that is it in a nutshell. Let's head over to the main program and start writing up some code to test this out and see how it does. So we start with our imports. We'll need gym. We'll need matplotlib.pyplot as plt. We will need numpy as np to take a look at the average rewards. We will need from reinforce Keras import agent, and from utils import plot learning. I'm not going to plot it here. You've already seen the plot at the beginning of the video. We're not going to bother with that again, but that's where you would import it. So if name equals main, then we want agent equals agent, alpha equals 0.0005, input dims 8, gamma 0.99, and actions equals 4. Layer 1 size equals 64, layer 2 size equals 64. And these are kind of what I found to work. So just a spoiler alert, policy gradient methods and the reinforce algorithm in particular is incredibly sample inefficient because we discard all of the memories at the end of each episode. So it doesn't make very good use of everything that happened prior to this episode. And 2, they are incredibly sensitive to perturbations in the change of the parameters. So what that means in practical terms is that as we do the gradient descent, as we vary the parameters in the neural network very slightly, that results in big changes in parameter space. Really what we're navigating here is parameter space rather than anything like cost space. And so that gives you big changes in the output of the model, and so it is a little bit unstable. I haven't done a whole lot of hyperparameter tuning. This gets a decent enough result. It doesn't quite beat it. I think in my PyTorch version it did beat it. There's always slightly differences between versions, but this forms a conceptual basis for other stuff like actor-critic methods and deep deterministic policy gradients, which we've covered here on the channel as well, and we'll do a couple more videos on them in the future. But just keep in mind that though you do not see the best possible performance, you are free to go ahead and tweak this on your own time and try to get the best possible results. I would encourage that and ask you to do that as well. So let's do our environment, Lunar Lander V2. Score history, of course, what we use to keep track of the scores and episodes 2000. The consequence of the sample inefficiency is that it takes far more episodes to converge to something reasonable, whereas in deep Q-learning, we basically have it solved within 150 to 200 episodes. Episodes done equals false, score equals 0, observation equals env.reset. While not done, action equals agent.choose action, observation underscore reward done, info equals env step, agent store transition, observation action, that's misspelled, obsre action, and reward. Observation equals observation underscore score plus equals reward, score history dot append, score blank equals, I don't think in this case I return anything, so it's agent.learn. And then we want to say print episode and I score 1f percent score, average score percent 1f percent mp mean score history minus 100, and that is all I want to print. So the end file name equals fname.png, whatever. Well, let's call it Lunar Lander. Lunar Lander.png, and plot learning, score history, file name equals file name, window equals 100. Okay, so that is pretty straightforward. Let's head to the terminal and see how many typos I made. All right, Python main lander. Okay, I forgot an equal sign. Okay, so let's just use nano. That is here. Activation equals, and here I have an equal sign. Okay, let's try it again. Okay, name advantages is not defined. Oh, I forgot the input, so that's why. That makes sense. You probably were wondering that. Let's say advantages equals input, shape equals 1, and that is that. Let's try it again. Hope it doesn't complain about Nope, it does not complain about the spaces, and it is running. I only made a couple typos, or pretty good for old Philly. So, okay, so it is running. You can see it runs quite quickly, and it is showing a little bit of evidence of learning. You can see that it's, it still has a negative reward, but it is going up over time. And you will notice if you watch it play for long enough, there is a fair amount of instability between episodes, and that is because, as I said, small perturbations in the network parameters result in large steps in parameter space, and you see it oscillate around over time. You could see that in the plot at the beginning of the video. But this is really the foundation for all of actor critic, deep deterministic policy gradients, proximal policy optimization. All of that kind of stuff follows from this basic idea of approximating the agent's policy. It is enormously potent and powerful in deep reinforcement learning, and it's really a very simple algorithm to kind of get started in deep reinforcement learning. It's much easier than Q-learning, despite Q-learning getting all the fame, because it is a pretty powerful algorithm. It's just a little bit harder to use. So I hope this was helpful. If you found it so, make sure to share. Hey, subscribe, and make sure to hit that bell icon, because I know only like 13% of you are getting my notifications. This is what my analytics tell me anyway. Leave a comment down below, and I'll see you in the next video.